So in this video, we're going to look at two concepts that we've already looked at so far. I introduced you to in other videos and line integrals and of course vector fields. Now the combination works as follows. If let's say that f is some vector field PQR with continuous functions and it is itself of course continuous based on that. And let's say that some smooth curve C is represented by the vector function RT, where T is between some finite values A and B. Then the line integral of f along C, so the line integral of f along C, which means of the vector field along this path C, is actually written as f dot dr, okay, which effectively with this with these definitions becomes, and effectively I mean of course that's in terms of calculations, f of rt dot product with r dash t dt, right? So this essentially is how we calculate the line integral of a vector field, in fact. Okay. Now, I would remind you, those of you who are taking engineering classes, how this is related to the work done. In fact, f dot dr is also referred to as the work done. Okay, and basically what you're talking about is F would be your let's say the constant force F, and moving an object from a point P to another point Q in space is F dot D, where D is of course the displacement vector PQ or whatever it might be. So, and suppose that F is PQR is a continuous force field on R3, such as the gravitational field, for instance, okay, or the electric force field, for the sake of argument. And in that case, if we actually end up with this this dot product of F with dr, that actually happens to be the force. So it's force times displacement is how you can think of it. Okay, so just aside for if you are an engineering student, I will be making some other videos separately for looking at applications, because the applications vary. This course is taught to different people, and most of the applications of vector calculus occur in engineering. Right, so let's continue with this. So here's an example. Compute f dot dr, where f is this vector field x, y, y, z, zx, and c is given here as x equals t, y equals t squared, and z equals t cubed. So so let's look at how we would actually compute this. So first of all, we have to look at our RT. Clearly, our RT is simply t squared, t cubed, t squared, and t cubed, and then we'll calculate r dash. R dash turns out to be 1, 2t, 3t squared, very easy. And of course, f of rt means that you parameterize. That's essentially the same thing as parametrizing. So x is t, y is t squared becomes t cubed, and y is t squared and z is t cubed becomes t to the 5, and z is t cubed and x is t becomes t4. So that's what we have. Now the rest is quite easy to do. So the integral above f dot dr is going to be from 0 to 1. This is our range of t values here. And of course, the dot product of t cubed, t5, t4 with 1, 2t, 3t squared dt. And that will become the integral 0 to 1 t cubed plus 2t6 plus 3t6 dt. Okay, so that's just t cubed plus 5t6 and that will just go to t4 over 4 plus 5t7 over 7. Zero to 1, and that comes down to 27 over 28. So it's as simple as calculating that. Okay, so I just wanted to quickly show you something very interesting here, a connection with something we've already done in a previous video on line integrals, in fact. So f dot dr is equal to a to b, as you know, that's just the definition. Let's see something interesting that happens. If we let f equal this pqr that you see here on the right, then what if we go along with that? What we're really saying is that we're calculating that's the integral. In fact, PQR dot product with in fact, and here of course we're assuming xt, yt, and zt. Okay, so then this would be x dash t, y dash t, and z dash t clearly, and that will be dt. Now if I take that dot product, let's see what happens. Something quite interesting, in fact, and something quite familiar pops out of this. So we end up with px dash t, so px dash plus qy dash of t plus rz dash of t, and all of these, of course, outside we have the dt. Now what does that look like? If you remember that, and of course here remember each of these pq's will be p is in fact, p is, what I mean by p is it's xt, yt, zt, because it's been parametrized, etc. Okay, and q is the same, and so is r. Now if you remember, that's the same as this integral. In fact, if I can show you, this was another notation for just p dx plus q dy plus r dz. In fact, that's what it is. So that's just an interesting connection between the two ideas. Okay, so one other interesting point is that something called the fundamental theorem of line integrals, which is related to the same idea, since we've looked at now vector fields and the connection between vector fields and how we calculate their line integrals, is to look at a particular vector field, which is the gradient vector field. So of course, if we had some gradient vector field grad f of some potential function, small f, then this, according to the fundamental theorem of line integrals, is simply f at r of b, okay, minus f at r of a. So the advantage of this theorem is that it sidesteps the integration completely, and in fact it is very similar to the fundamental theorem of calculus, which I hope you can possibly remember, but if not, here's a quick reminder. So when you have f dash x dx, it's equal to fb minus f at a. So that's the fundamental theorem of calculus, which is actually part 2 of the fundamental theorem of calculus. So this on the side here, just a reminder, but this is, as you can see, is very similar to this idea. Okay, so let's look at this example of using the fundamental theorem of line integrals. So here we have this rather straightforward function of x, y, z. In addition, the path we've chosen is that we let c be any path. Only thing we note are the important things, which are, it's not the parameterization that is critical here. In fact, if we're using the fundamental theorem, what's important is the starting and the end point. And those are as given here. So this simply, according to the theorem, we don't need to calculate the gradient. We don't need to do anything except just calculate f at, in fact, the starting point, which is 1/2 2. So that's just going to be 1/2 2. Because if you think about it, let's say RA is the starting point, and it will have to be 1/2 2 then, no matter what R is, because that's the starting point. And we don't really care, irrelevant of the path, the starting and end points are as they are given. We can't change those. So those will be those 2 points. So that means it boils down to just f, second point first, pardon me. Sorry, so it's 2 1 minus f at 1/2 and 2, which boils down to really just cosine 2 pi plus sine pi, okay, minus x, that will be, so what is it, 2, 1 minus 1, so it'll be 2, 1, 2, so it'll be just 2 here, okay, and minus 1 squared is just 1, so it's this, and then minus f of 1/2, 2, so that's going to give us, 1 is going to give us cos pi again, that's 2 pi, this one is cos pi, and then we have sine of pi over 2, okay, and then minus, we have 1 times 1/2 times 4, so that's 2, okay. So that will then be cos 2 pi is 1, sine pi is 0, so it'll be just minus 2, cos pi is minus 1, so it'll be plus 1, minus sine pi over 2 is 1, minus 2, so that becomes, cancels, minus 3. So that's it. It's as simple as that. We'll stop.